In this exciting episode, we will be learning how to linearize a graph. We're going to particularly look at a parabola, but this generalizes up to any other sort you want to look at. And we're really going to look at not just the mechanics of how you do it, but also why it works. And it's really that piece that will let you apply this generally to any of the graph shapes that we work with. So I have a little flow chart here that I made up for you. So there it is. Here's the basic flow of how we deal with data in physics. We do an experiment, we collect data, or we get it handed to us. So there's our step one. We graph that data. We make a large, nice, full-size graph, full-page graph so that we can see what's going on. We have to plot our data carefully so that we can understand the shape of the data. Then we ask the simple question, is it a line? There are two options. If it's a line, great. Go find the equation, and you're done. The goal is to get an equation. We want to find the relationship between the variables, and what we mean by that is go find the equation. But if no, then you have a little bit more work to do. We actually have another graph to make. Excuse me. So if you graph your data and it's on a line, you have to look at it and say, okay, what is it? For this, we use the chart that was provided at the end of that reading that I've asked you to memorize. I've asked every class to memorize that chart. You memorize it so that you can do this. You look at the shape of the graph and say, oh, okay, here's my graph. Great, that's a line. I know it's a line, so I know the equation is here. I can find that. Perfect. You look at your graph and say, oh dear, it's not a line. That looks like a parabola. So we know immediately that the equation looks like this. K, or whatever constant you want to put in there, x squared. We know that this is the equation, and this will tell us how to linearize it. There's a whole chart of them. I'm not going to go through all of them here. There are other videos for that purpose, but that's the idea. Look at the shape, guess what the equation is going to be, and this is the key. It's a guess. Might be wrong. So we're looking at parabolas this time. So if I look at my graph data and it looks like a parabola, I guess this is a relationship. I look at the chart and the chart says to linearize, which is to make a line out of it. It's a made-up word, don't worry about it. To linearize, we want to plot y versus x squared. It's important to realize that here we plotted y against x. But in our test plot, we're going to plot something different. We're going to put y against x squared, and our hope is that this comes out in a straight line, because then we ask, after we've made our test plot, we say, is it a line? If it is a line, yes, we go find our equation. If it is not a line, then we look back and say, okay, it wasn't a parabola. What was it? Was it a cubic? Was it a quartic? Was it something else that we weren't anticipating? Is this really an exponential masquerading as a parabola? But if you see this shape and you're doing physics, odds are it's a parabola. So hopefully we don't have to get stuck in this circle for a terribly long time. So let's look at why this works. Here's the equation we're going to play with. Okay. The idea is that we need to transform this parabolic equation we need to make it look like y equals mx plus b. We can actually generalize this a little bit more. We could have a constant term out here. We cannot have a linear term, right? But we can take this and try to generalize it to look more like that. So here's the trick we're going to do. We're going to create a new variable. You can do that. You just have to define it. So we're going to let our new variable z be equal to x squared. So we have this new thing, z, it's equal to x squared. We're now going to rewrite this equation making a substitution. So we have y is equal to a z plus b. Now as we look at this, the game has changed. If we were to write a statement for this, we would say y is proportional to x squared. That's what we would say. That's not a line. But here we would say y is proportional to z. That is a line. This is exactly what you would say about a line. Y is proportional to z. So this should result in a line. That's why we can go ahead and find the equation. This is why the trick works. If you want to look at another example, y is equal to a over x. Plus b, not plus b, whatever. We'd write our statement. Our statement would be y is inversely proportional to x, because it's in the denominator. If we simply let z be whatever has been done to x, if we say z is 1 over x, now we can write this and then rewrite it. We can say, okay, well, z is 1 over x, so y is a times z. Well, to that, we can say y is directly proportional to z. That's a line. So when we plot this, we should actually find that this is a line, and we could find the equation of that line. The big trick here is that z is 1 over x. So all you have to do is change variables, and this will work. So let's go look at some numbers. I've set up a data table here, and I've actually already used a computer to plot it. So we look at this and say, okay, it's definitely not a line. It looks like a parabola. So it's a parabola. We're going to follow our flowchart. So look back, we collected the data, we graphed it. Is it a line? No. We use the shape to guess the equation. We think it's a parabola. Okay, so we're going to guess the equation is y is equal to ax squared. It looks like we're going through 0, 0. We are going through 0, 0, so we don't have a constant term. So there it is. We're going to let z be x squared. What do I have on the next page? Okay, so we need to figure out what z is so that we can make our new plot. Okay, so y is equal to a z. That's a straight line, but we need to know what z is so that we can actually graph this thing. So let's go over here, make a new column. Z. Well, z is x squared. So if x is 0, z is 0. If x is 1, z is 1. If x is 2, z is 4. X is 3, there's 9, 16, and so on and so forth. So here are our new values that we're going to plot. So we now need to plot y versus z, but we're keeping in mind that z, okay, so this is incognito here. That's really x squared. We're going to plot y versus x squared instead of y versus x. And if we actually do that, going over here, here are those z values. We look at the graph, y versus z. This is a straight line. Whoa, look at that. And we remember that, well, that isn't really z, that's really just x squared. So when we write our equation for this, okay, y is equal to mz, that's our variable here, z, but we keep in mind that really that's just x squared. Z is x squared. So we found the equation of this line, but this line is really a parabola incognito. Right there is the equation we will have found. So this is a trick that enables us to find the equation of a parabola or an inverse curve or any of these other things where we would not normally be able to do it. Well, we wouldn't be able to do it by normal algebraic means.